So tonight I have the pleasure of introducing our speaker. Dr. Jan Newton is a senior principal oceanographer with UW's Applied Physics Lab, as well as an affiliate professor with UW School of Oceanography and the School of Marine and Environmental Affairs. She's also the executive director of the Northwest Association of Networked Ocean Observing Systems, co-director of the Washington Ocean Acidification Center, and co-chair of the Global Ocean Acidification Observing Network. So I'm very happy that she can be here and was willing to take time out of her undoubtedly very busy schedule with all of those long titles. So with that, Jan, welcome, and please take it away.
Oh, thank you so much, Geraldine. I really appreciate being invited here, and to all of you who are, experiencing the effects from the storm. I hope this can take your mind off of it. And so I'm going to start my first slide here and share. And slideshow. There we go. So the story I want to share with you is one that goes over different scales. As my title says, global issue on local scales. And we're going to talk about all of those. And I have a lot of titles, but they're really interrelated. And so you see them listed there under the University of Washington. And we'll talk, I don't want to make too many acronyms, but they're different scales, right? Washington, Northwest, and then global. And so if I'm using those acronyms, just remember that the W stands for Washington, the N stands for Northwest, and the G stands for global. And it's my opinion that it's really most powerful when we integrate back and forth across these scales. So I find my work very connected, even though it is diverse. All right, we're going to talk about ocean acidification. And this slide, to me, is such a beautiful slide. Obviously, it's home. And what I love about it is you can see the land, the ocean, the clouds, and you can see the snow even on those mountains. But you can also see that atmosphere. And we know how important that atmosphere is. And one of the things that is so critical about ocean acidification is understanding that the way that the carbon dioxide is interacting with our atmosphere and interacting with our ecosystem has changed. And you see all of the actors here. You see the phytoplankton, that green stuff in the blue waters. You see the waters, you see the atmosphere, and you see the landscape that we humans live on. So what is oceanography? You know, it's after 6, or what is ocean acidification? Excuse me. It's after 6 o'clock, and I'm not going to go into equations, though I'm happy to if someone wants to. But to really understand ocean acidification, it's basically this: carbon dioxide from the air added to seawater changes the chemistry of the waters. And if you want to go beyond that, it's reducing the pH and the carbonate levels in the ocean. And we'll talk about why those are important. But here's the evidence for that. It's extremely strong. And the Intergovernmental Panel on Climate Change, over the course of my lifetime, I've seen it go from overwhelming evidence to being virtually certain. And so here you see 3 plots versus time. And so the black line, that's the CO2 in the atmosphere as recorded on Mauna Loa. And so that's the Keeling curve. We've all heard of that. But these other colored lines, the green, blue, and sort of golden, are from other areas, Bermuda, Canary Islands, and Hawaii. And you see that they show that the partial pressure of carbon dioxide has increased, and they all have the same slope. The pH has declined, and again, they all have the same slope. And the carbonate has also declined. And that is that the trend is consistent all across different ocean basins. And that's really telling us that we've got an atmosphere that has a lot of CO2 in it, and it's equilibrating in the ocean from the atmosphere. We see that atmospheric increase and the same slope increasing in the ocean. And the amplitude of those squiggles is the seasonality. So phytoplankton take up carbon dioxide and they release oxygen. And so when that's happening during the summer, the drawdown, it's those lower values. And then when there's not so much photosynthesis and there's compelling amounts of respiration, that's the higher levels. Okay, so that's really the breathing of the planet, if you will. And so that's the CO2 record, but the carbonate chemistry is so linked that it's linked to basically when CO2 goes in seawater, it forms carbonic acid, and then that quickly dissociates, and there's these protons that are generated, and that's what defines what pH is. And so the pH declines, and we know how important pH is. And then there's carbonate, calcium carbonate. You've all heard of calcium carbonate and how those form the skeletons of plankton and then also shellfish. Well, the availability of the carbonate declines. All right. So that's the chemistry. And so now what I want to do is get this to advance, is to talk about what's going on in terms of biology, just really briefly, but to show you, here's all the chemistry changes that we just talked about, abbreviated for the CO2, the bicarbonate ion, the carbonate, and the pH. Biological effects, well, actually more CO2 in seawater could actually increase photosynthesis if phytoplankton are limited by CO2, which is actually somewhat rare, but that could be an effect. But it decreases the shellfish calcification because they use these ions. And then pH is kind of a master variable that can have changes in physiology. And I don't have time to go in depth into all of these biological effects, but for any organism, they are sitting there in the context of temperature rises, oxygen decreases, and then other stresses like overfishing, pollution, oil spills. So we think of ocean acidification as a multi-stressor. People talk about a multi-stressor ecosystem. So before we move on, I want to define one more term here, and that's this little symbol, omega. It's a Greek letter, alpha, omega. Omega is what chemists use to define the saturation state. And so we're going to talk about the saturation state of two different calcium carbonate constituents. One is called aragonite and one is called calcite. And so I'm just going to abbreviate that with this little omega sign. And anytime you see omega, just know that's the availability of the carbonate, and we're going to use the aragonite, and that's what some people call them, the building blocks for calcifying organisms. Okay, so here is something produced by NOAA and colleagues. Surface ocean pH changes since the Industrial Revolution. And so if I can reduce this, there we go. Here's the pH scale down here, 7.1, 7.7 at this midpoint, and 8.3. Now it's really important to remember that pH is on a log scale. So a 0.1 difference in pH is going to be a 30% change. And so that's not very much, 0.1, but a 30% change, you can definitely, when that happens to your bank account, that there's something happening. All right, so there's been changes since 1850 projected out to the end of the century. And some of these changes are quite large. But what we also have seen is that early vulnerabilities are around upwelling areas that always had lower pH because of the increased respiration that's down at depth, and the upwelling brings those waters up to the surface. So anyways, upwelling areas have always been sensitive, but they are projected to be even more so because you have a natural signal and then you have the human signal. And when you put them together, even though this one's bigger than this one, when you put them together, that's when you can start to overtop thresholds. All right, so we live in an upwelling area, Washington waters. And so this was recognized by scientists and shellfish growers that Washington waters are particularly vulnerable to ocean acidification because it was appearing decades sooner than anticipated. And the scientists started to recognize that the coastal upwelling, the fact that we've got a lot of nutrients and a lot of organic carbon and a lot of decay of that organic matter, we had a lot of respiration going on in the water. And so we're getting those results sooner than anticipated. This is a really incredible picture. I want to introduce you to the 4 people in the picture if you don't recognize them. But this is really, these leaders really is what spurred the action. Here's our former governor, Christine Gregoire. Here is Billy Frank Jr., a beloved and most effective tribal leader. This woman here in the green is Jane Lubchenco. She was the former administrator of NOAA. And the gentleman talking is Bill Dewey with Taylor Shellfish. And he was explaining how things weren't working the way that they used to, right? And so here you have the state leader, a tribal leader, and a federal leader listening to an industry leader. And they realized that this is important. Washington needed to get out ahead of this. And so Governor Gregoire called for a blue ribbon panel in 2012, and it assembled about 30 people from government, from science, from industry, from NGOs, all from the tribes, all across different sectors to come together and create a report that said ocean acidification from knowledge to action. And this is the URL where you can access this report and a subsequent addendum that was published 5 years later. And also this report, which is actually the appendix to this book, but it's thicker. This is a scientific summary of ocean acidification in Washington's marine waters. And so it was everybody working together that produced these assessments of status and what we should do about it, what actions we should take. Some of the actions they wanted to do were to establish an advisory council, the Marine Resource Advisory Council. This is chaired by Martha Kongsgaard, and this continues to today. And they meet regularly and evaluate the new evidence and talk about what needs to be done. They also established the Washington OA Center at UW that I co-direct with Dr. Terry Klinger of SMEA at UW. And they directed the center to implement some of the actions from the Blue Ribbon Panel recommendations. And so some of those recommendations were science recommendations. So one of those recommendations is to monitor ocean acidification and also the biological response. And so not just looking at the chemistry, but also looking at biology measurements. And we're doing a few of those. One is to look at the plankton, all right? Plankton, you can think of them a little bit like first responders because they, of course, live in the water and they have really short life cycles. They don't live that long. And so they are embedded in the water, and their response is to that changes in the chemistry. So they're good indicators. We're also doing some things like environmental DNA that tells us what has been in the water. We're measuring trends over time that we can see from buoys. We're also looking at trends over space that we can do from ship surveys. And we're working a lot with existing networks, including shellfish growers. Okay, So here's an example of one of our seasonal surveys. We go all throughout the Salish Sea. We have other surveys that come out onto the coast. And then there's work up in the San Juan Islands that's also being done by Friday Harbor Labs. But these seasonal surveys measure these things, the carbon variables, oxygen, nutrients, chlorophyll, different kinds of plankton, different calcifying organisms like pteropods and crab megalopi, their larvae. And we're looking at whether their shells are dissolving or not. And then, of course, things like temperature, salinity, weather, looking at methane, and then also fish using acoustics. And what's really awesome on these cruises is like I'm taking an oxygen sample at the same time from the same water that somebody else is taking a sample for dissolved inorganic carbon at the same time that another person is doing a net tow to look at the plankton. So it's all being done at the same time. And I'm really happy to say that right now I'm here at Friday Harbor Labs and I'm teaching a class with others, pelagic ecosystem function. And some of my students are on this webinar and we've been doing those same measurements up here in the San Juan Islands this fall quarter. So it's really great that we're getting this database and it's allowed us to look at how diverse different areas of Puget Sound are. And so we're going to talk about our friend Omega aragonite and look at how its characteristics are at different times of the year, February, April, July, September, November, as well as in the surface waters and at depth. Okay, so we're going to look at all these different locations and we're going to color code the Omega aragonite. When it's 1, that's saturation. Above 1, it's super saturated. That's great. There's no problems. Below that, it's undersaturated. And that's when you can start to have shell dissolution. So when you see that orange to red, that's not such great conditions. Okay, here's the data based on, I think, 3 or 4 years of cruises. What you see is that there's a lot of different colors. Some show very similar values from surface to deep. Others show a big difference from surface to deep. And then there's much change with season in some places, less so than others. And what this is telling us is that different parts of Puget Sound of the Salish Sea are reacting differently because of their unique oceanographic characteristics. Whidbey Basin and Hood Canal have strong stratification, 2 layers. And so if you're a pteropod, it's great to live up here during the summer, but really bad to live down there. At the same time, if you're a pteropod in the Eastern Strait, it's kind of so-so no matter where you are. And less so in say September. So it's really interesting. It's really important, I think, to get a handle on how Puget Sound is, what the patterns are, so we can better understand biological responses. And so here is some of those biological response views. One is, these are the pteropod shells. These are little tiny microscopic, like a pencil dot shells, plankton. And because their shells are made of aragonite, they can actually show signs of dissolution, this pitting, if the conditions are bad enough. This one is from La Push off the Washington coast. This one is from Whidbey Basin in Puget Sound. And the pitting is so bad that there's actually a hole in the shell. That's not a good life history strategy to have a hole in your shell. So there's more stress on these organisms. Nina Bednarsek in a paper that is, I'm gonna ask Geraldine to put the URL for it because you can access it from the Washington OA Center website. The pteropod paper tells us that there's different patterns over time and space, but these organisms are persisting. So even though we're worried about these conditions, there's persistence of this species, and we want to get to understand better how this is affecting the ecosystem. And it's important to get this understanding ahead of the curve now and not wait till the end of the century. Okay, the second thing that they asked the OA Center to implement is forecasting. So our buoys, our surveys, they only are at different points or at different times, and it doesn't give you comprehensive information every day all over the place. People can make computer models that estimate these patterns. And so here, once again, we have aragonite saturation, the omega, and it's color coded. So now 1 are these cool colors, less than 1 are these cool colors. And so the blues, and look at that. Here's Whidbey Basin, here's Hood Canal. That's where the pteropods had the holes, where they had the most dissolution. And so why are these places like that? Well, there's a lot of organic material that goes into these different fjord-like basin, in the case of Hood Canal, and somewhat restricted basin here in Whidbey. Each of these have less circulation than some of the, like the main basin that just gets whoosh, whoosh flushed, and even some of South Sound, which is really flushed from the tidal energy and mixing energy from the Tacoma Narrows. So in any case, we're learning more about the distribution of where the patterns are worst, and also how that changes in time. And what's really exciting about this work that Parker McCready at the University of Washington has done, he hosted it on this NANUS website, and it's a forecast. So not only, well, this is an old slide, but if I made this today, you would see, I don't know what day it is today, but you would see today's, tomorrow's, and the next day. So you see the next 72 hours. And it's really helpful for shellfish growers to know how things are changing with time. And here is a simulation that Parker has made down at Willapa Bay, which is a really important oyster growing area. And we've learned that, again, here's our friend Omega aragonite. The Columbia River, which is fresh water, has more alkalinity. And so that can affect the saturation state of omega. And so some of this Columbia River water can curl around and come into Willapa Bay when the winds are blowing to the north. And when the winds are blowing to the south and the plume goes south, there's actually upwelling that brings in low aragonite saturation state water to Willapa Bay. So Willapa Bay is actually a really interesting ecosystem for growing oysters, and it's very sensitive. Sometimes it's good, but it doesn't take much to tip the apple cart, if you will. So these kinds of forecasting tools are being used by shellfish growers, managers, and others, and scientists to understand better. Okay, the third thing was to understand biological responses, and on Washington species. You know, some of the first OA biological assessments were on tropical fish, like the little, the Nemo fish, I forget his name. Anyways, so we funded research on Dungeness crab, on krill, by NOAA and by UW, Paul McElhaney, Julie Keister and her students. And they found things like delayed development, reduced survival. And we've been lately turning our attention to salmon, forage fish, and harmful algae. And so trying to encompass more of the food web by going to these higher fish trophic levels, but looking at the intermediate forage fish level, and also looking at harmful algae. There's a published results from lab experiments that show that ocean acidification can make harmful algae even more toxic than they are. So we want to study that in the field. And so most of this research is still under wraps, still being investigated, but the salmon research was recently published by Chase Williams and his colleagues. And what it showed is that juvenile coho salmon show changes in their sensory behavior. Their ability to smell and detect the predators as well as the prey is not that good when you have higher CO2 in the water. All right. So that's really interesting. And this is something we were studying. Well, Chase Williams was studying. We were funding right before the pandemic. You notice this was published in 2019. We funded some more work to see whether their detection of their natal streams would be affected. And unfortunately, the pandemic has really put a damper on this research, but we're hoping that as people have access to their labs again, that we can continue this work. And the URL is there for the fish paper, if you want to read some of this primary literature. Okay, and then lastly, to work with the shellfish growers and the hatcheries working as working laboratories and seeing what they see. All right, so we've talked about ocean acidification. We've talked about how it's a global condition with local effects. And that's going to be different depending on which shoreline you're standing on. Washington State, Fiji, the Caribbean, or New Zealand. Each of these has different substrates, different species, different cultural dependencies, different resilience factors. And so what's important to get an understanding of ocean acidification on a global scale is to do that on local scales, but to do it globally in a way that's coordinated. And this is really important whether you care about the health of the planet or the future of shellfish. And so at the same time that people were coming together in Washington State, and those talks led to the OA Center and the Marine Resources Advisory Committee, people were coming together on a global scale to think about how we could better coordinate OA observations on a global scale. And so another thing was born, the Global Ocean Acidification Observing Network, or GOON, as we call it. GOON's a collaborative international partnership, and it's designed to do three things: document the status and progress of OA in a variety of environments, understand the impacts of ocean acidification on diverse marine ecosystems and societies, and support forecasts of OA conditions. All right, so this started and the scientists really came together to make this because they realized we need local through global scale observations in order to get either correct. We can't understand Washington if we don't understand the global context that Washington sits in, but also we're not going to understand a global situation unless we have the myriad mosaic of all of these local stories. And so the issue demands our coordination, network skill, and open analysis. But this is more and more possible these days. I mean, I'm talking to you in your homes all over, and it's easier to do this global coordination as well. All right, I think I already made those points. So the community defined the how this should come together, what should be measured, how to do data quality assurance, how to distribute data, and how to integrate the program. And as people came together, it became obvious that we had some people like Richard Feely, who is in Seattle at the NOAA PMEL lab and an international leader and superstar of ocean acidification, saying like, well, we need the highest quality data in order to see these trends because the trends aren't that large, but they are measurable if we have high quality data. And then you had biologists sitting there and saying like, well, we're trying to understand how OA affects biology, and we don't need these measurements out to the nth decimal place. We just need like the first decimal place, and that works for us, but we want to understand that to understand the ecosystem response. And we realized that everybody was right, but what we needed to do is define two quality objectives, and these have been called climate data, weather data. But what was really exciting to me is to see how the community came together and recognized that things need to be fit for purpose and that we can do all of that together. All right, and so go on, define all of those requirements. But the last one on here is the intellectual infrastructure. And that is the one that is always overlooked and, in my mind, the most important. Sometimes you can get money for buoys, but you can't get money for the people to analyze the data or to train the next generation. And so Go On put a major emphasis on capacity building. And this is what, in 2013, 1 year after Go On was formed, this is how many people were there, how many countries, 150 scientists from 31 countries. This is how we look today. And actually, I heard that we're over 900 from 105 countries. And you can see that it's a much better globally distributed map instead of focused on North America and Europe. And how did we do this? Well, we came together and recognized the need to build capacity. This was a meeting in 2016 in Hobart, Australia. And this is where we started two things. One is the concept of mentorship program, and the other is organizing ourselves according to regional hubs. And so here's our capacity building stories. We have a mentorship program that's called peer-to-peer. That's science humor, peer-to-peer, anyway, the way it's spelled, as well as assistance and this new go on in a box kind of concept. And so thanks to the Ocean Foundation and the Ocean Alliance, a lot of these trainings have gone on around the globe, really increasing capacity. This is the arrangement. We now have 8 regional hubs throughout the globe, and these are all active hubs of people organizing together. There's a North American hub here, and you can find all that information on the Go On website. We have a data portal for discovery of where OA data is happening, but none of that matters if all that's done is the science and we keep it to ourselves. It has to reach society. And the United Nations established some sustainable development goals, and 14 is what they call life below water. They also established a decade of ocean science for sustainable development. And this is really putting the flashlight on how important the ocean is to society and how important it is that we translate our information to society. And so Go On has played a role in helping with this indicator for ocean acidification. And as part of the SDG, Sustainable Development Goal. Here's a lot of other programs from the Commonwealth, the World Meteorological Organization, and the role that Go On scientists are playing in order to integrate OA information to policy. And last year, for that UN Decade program, Go On proposed a program called Ocean Acidification Research for Sustainability that has now been endorsed by the United Nations. And it really aims to amp up the effort to provide society with evidence needed to understand how to monitor, mitigate, adapt to OA. And so this is going to be something we're really focused on for the next 10 years. This YouTube URL is when the UN Special Envoy for the Ocean, Peter Thompson, endorses this OARS program. And here's what OARS aims to do by 2030. Work on getting high quality data, science to action, recognize that, Washington State, right? Long-term ocean observing systems, impacts to biology, societally relevant predictions, making sure the public is more OA literate, and then allowing countries to have the information they need that can aid them to make their respective legislation in their nations. All right, so let's see. I'm going to focus on this one a little bit with the last example that I want to share with you. Societally relevant predictions of the impacts of ocean acidification will be freely available. So I brought you from the shores of Washington now out to the globe and how it's important to do what we do on a global scale. And now I want to take you back to Washington with an example of doing societally relevant predictions of OA. So I'm really proud to be part of a team that you see here, many members that got an award from NOAA to look at an integrated social, ecological, regional vulnerability assessment. Okay, regional vulnerability assessment. How vulnerable is the Olympic coast to ocean acidification? And in order to do this, we integrated social science and ecological science. And this is done with UW, NOAA, other university, and 4 coastal treaty tribes, as well as the sanctuary in the Olympic National Park, everybody working together. And so integrating the social science and the natural science. So understanding what's important to the tribes. And Melissa Poe with Washington Sea Grant leads this effort. And then understanding what are the patterns in the biology and where is it forecast to go by the end of the century. And then putting that all together to inform the tribes, inform the scientists, sharing that so that we can work together. Okay. This is our, what we call the wheel, and it's the processes that we figured out how to do this regional vulnerability assessment. And I know it's a lot of words, but the blue steps are the social science steps. The orange steps are the ecological, oceanographic and ecological steps. And then the green steps are the ones that we do together. So first, define your scope. Then understand the social importance of species and the role in well-being for the tribes. Then analyze the variability in the chemical and biological data, project what the future oceans are going to be, and then assess how often, the frequency, how long, the duration, and where the location where we're going to see harmful oceanographic conditions. Take all of this together to evaluate the risk to the ecosystem and resources that are important to the tribe, then analyze the socioeconomic conditions and the equity, and with all of that, assess the social vulnerability to ocean acidification. And then the rest of this wheel is working with the local decision makers to figure out strategies for how to adapt. Because ocean acidification isn't going away as much as we would like that to happen. And we really need to have information so that we can be prepared and respond. And so this has been a journey, a 3-year journey that we're still immersed in. And I want to just give you one real quick example of how this, I think, is really working. And it's changed my understanding of how doing science in the context of social science is really powerful. So how do we evaluate risk? I mean, my gosh, there's so many species and there's so much spatial variability and all of that. But because Melissa and her team had worked with the tribes to understand what's important, there's a lot that's important, but we picked 4 species with different life history patterns: razor clams, Dungeness crab, olive snails, and Pacific halibut. And then we took all of the existing observations, and of course, it wasn't as much as we needed, and it's on different scales and all of that, but we synthesized what we had. We looked at patterns, and then we looked at model output for the present. Whoops, I don't know why this is going on its own scale. We looked at the model, forecast model output, present and future. And then we evaluated different assumed thresholds and said, well, if the pH was this, how bad would that be? And where does it look bad, et cetera, for different stressors? Well, that yields a whole bunch of plots, over 300 plots. But what we are doing now is building back these 4 stories, okay? And razor clams are really important to the tribes. They settle on the Olympic coast in April and May, and that's a really critical time for them. All right, so of course the whole year is important, but when those larvae are settling, that's when we really need to understand the conditions. So now we've narrowed it down. Instead of looking at everything, we've looked at what's going on, where razor clams settle during April and May. And that's a much more manageable way to assess something and understand its vulnerability. And it's grounded in the social science of what's important to the tribes. Okay, so last data slide, but it's a doozy. Okay, so this one on the left is the future minus the present conditions, the changing conditions from the end of the century minus how it is now. And we're looking at the omega, the saturation state of aragonite, which is important for a razor clam, on the bottom, on the seabed. And we're looking at it in May. And so here is that delta bar. And you can see that a change of 1 is this dark color. Now, a change doesn't tell you everything, right? Because you could be at 3 and you get down to 2 for omega units, that's still okay. But if you're at 1.5 and you get down to 0.5, that's really a problem. But this allows us to see where the change is greatest, because sometimes organisms, you know, they're stressed when conditions change. But then this map over here has all of these different symbols for different organisms, for different measuring things, but razor clams are these diamonds. And this scale now is the percent of the month that is undersaturated. So if you're undersaturated in aragonite 100% of the time or 75% of the time, that's these darker colors during May, the percent of the time during May. And what we see for these razor clam locations, that we're approaching some fairly dark colors. So like around 50% to maybe more around 40 to 30%, but still that's a big change in the percent of the month when we have these undersaturated conditions. And so by understanding the conditions that are important to the species, that are important to the tribe, that's the stories we're working to develop. So that's the story I've woven for you. I know we've gone around and dabbled in a lot of different things, but I hope it fit together somewhat and piqued your interest in terms of how it's important to study on a local scale. It's important to study in a global context and make sure that we're building capacity. And it's important that we study not just the science, but the science in the construct of society and the resources, the cultures, the economy, and the health that depends on the ocean, because ocean truly is our home. Earth would not be the same without the ocean. So with that, I'm going to ask for questions, and I'm going to see if I can see you all again. There we go. All right.
All right, thank you so much. I'm gonna scroll back through the chat here. Let's see. The first questions are about the data sampling. The first one is, with synoptic sampling, you get great data in one time frame, but is there diurnal variation? Should you be doing synoptic sampling 4 to 6 times a day?
Yes, and that's why we have the buoys. That the buoys are out there 24/7, and we do see diel patterns. Yes, and so these buoys take profiles several times a day, and yeah, that's why that's a really important strategy. The buoys, yeah, not all buoys are the same. these are very special buoys because they profile. So like they take a sensor package that's up at one depth, and there's a winch on there, and it brings it down to the seabed and then back up to the surface and then parks it down again. And so it does that several times a day. And then you can string that data together and see diel patterns, day-night patterns, and really get a better handle on seasonality. The cruises are valuable simply because you can't take zooplankton net samples on those buoys, automatic. Well, actually, that is actually starting with some of these very fancy things like imaging flow cytobots. Like there's one here at the Friday Harbor Labs that takes water samples for plankton, but those are super expensive and we don't have them everywhere. So it's a mix and everything is a compromise, but we try to stack our bases. Yeah.
The next one is, there's always a tension between modeling and monitoring. What would you wish for? More monitoring, more monitoring, better modeling? Is it a good spot?
It's the sweet spot where you have both. Terry and I talk about the strategies that the Washington OA Center has as the three-legged stool. And if you kick out any one of those, you're not going to be as strong. And the modeling is really important because it fills in the gaps that you can't see with monitoring. But the monitoring is really important because it helps to calibrate and verify the modeling. And if we didn't have those data, the models wouldn't be nearly as accurate. So they need each other. And then also the modeling can tell us where I hate the word hotspot, but I can't think of a better one, where the places are that have the most severe conditions that you might not see. Like maybe there's small areas. We know Whidbey Basin, Hood Canal, but by looking at the models in detail, we can find some things that we can't monitor everywhere. But the modeling allows you to see places where, hey, we should do this one less and do over here more. So they're peas in a pod. They're hand in a glove. I don't know. I don't have the right analogies, but we need them both.
Do you use underwater gliders to collect information, and can these gliders be used in Puget Sound?
Oh gosh, yes. Off the coast, we are using underwater gliders, and I'd like to direct you to the NANUS website. And if you go on to our NANUS visualization system, or NVS, and then look for the little icon on gliders, you'll see some very recent data from a glider on the Washington Shelf. Gliders are measuring things like temperature, salinity, and oxygen, but then scientists can have developed algorithms, equations that help you to calculate things like pH or aragonite saturation state from those variables. So you actually can eventually get fields of OA variables. And so it's a really powerful technology. Unfortunately, they're great off the coast. Unfortunately, they're not so hot in Puget Sound. So a glider undulates throughout the water column, and then it comes up, sticks up its tail, and transmits its data to the shore, and then it goes and da-da-da-da. And so it's doing that. And we've lost two. And actually in Saratoga Passage, and we think they were just ship strikes, boat strikes. It's just that there's too much boat traffic in a confined space in Puget Sound to use gliders effectively, at least the gliders we have at hand. There are people, Dana Manilang at the Applied Physics Lab, who's looking at using different kinds of autonomous vehicles that maybe are propelled and don't have the same requirement to surface, where they can get hit by boats and crinkle and fall to the seafloor. And it's really depressing when you lose something like that. And so ones that can dock to stations and things like that. So, there's no limit to the technology that could be developed to this. There's obviously a limit to our cash flow for funding new technologies, but let's see what the future holds for us. Yeah.
Given the differences in data quality needs, are there opportunities for citizen scientists to assist?
Ooh, that's a really good question. And it's one I've struggled with a lot. It really is, because measurements for things like temperature and salinity, it's relatively straightforward to get lower priced equipment to do that. But pH sensors are not great. In fact, the X Prize held a competition to try to make better low-cost pH sensors, and I'd say it was moderately successful. The thing is, you need 2 carbon variables in order to calculate. Okay, so there's 4 carbon variables. There's PCO2, oops, let's do this. PCO2, pH, dissolved inorganic carbon, and total alkalinity. And if you have any 2 of those 4, you can calculate the rest, and you can calculate things like omega saturation state. If you only have 1, if you only have pH, you can't do that. And right now, PCO2 sensors or sensors for any of those other ones are really cost prohibitive. So I struggle with that. What I think citizen scientists or community scientists can do is really help us with biological observations, because the chemistry is one thing, but what we really want to understand is how biological populations are changing. And that could be kelp, which might be increasing because there's more CO2, or that could be calcifiers that might be decreasing because there's not enough saturation state for their shells. And so understanding how that changes in time is really important. And that's where community scientists are so powerful. Now, the problem with that is OA isn't the only thing that's happening, right? And so it's multiple stressors. So how do you know if you see a change in kelp or a clam that it's due to OA and not due to changes in temperature or changes in salinity or changes in people trampling? It's really hard to pin that down. But on the other hand, having that information is still so incredibly valuable. And at some point, it doesn't really matter which one is doing it. It matters that we know that these things are changing. So that's my best answer on that. But it is something I struggle with. Yeah.
We have a couple comments here I can share. So happy to see you using the UN SDG as a framework. Bravo. And you might look at the UN SDG for ending hunger, because shellfish is food and ocean acidification affects food.
Yeah.
And then the next question, do you have any economists working with you on the social science end? The economics of ocean acidification is incredible.
Yes, I don't personally. That's a really good statement. I know there are a lot of economists that are starting to work on ocean acidification and just ocean health in general for the reasons you state. I mean, it's seafood is food. Seafood is life, and it isn't just seafood. When you see those changes in the salmon's ability to smell, there's a lot at stake here, and so. So anyways, there are economists that are engaged on this, and that's something that ORS really wants to promote. And so, yeah, it's a really important thing. And I think it's so hard for, you're trained as scientists to do your thing, and this, interdisciplinary oceanography, when I was cutting my teeth, was a chemist working with a biologist. Woo, that's interdisciplinary. Well, okay, gang, there's this whole other world out there. There's this thing called society. There's this thing called economy. And that's where we can really stand to make some some changes? These are great questions.
Do you think that the gliders might be recoverable from Saratoga Passage?
No, because we don't know when it happened and where it happened. We just know when it called home last, and then we know that it never called home again. So yeah. And it's not that big, so you can't detect it with sonar.
Got it. What can ordinary people do to help with this problem?
The most important thing is learning about it and talking to your circle of your community, your family, your friends. It's the understanding of the ocean tends to be so foreign to some people because, you see Puget Sound and it looks beautiful. It's blue and pretty and all of that. And I think people understand like plastic trash and things like that. They know that those things are bad, but understanding how, carbon dioxide and our role with that and everything, it's a little more esoteric. And I think there's a lot of, how society is so divisive these days. But I think what really has been a boon for the ocean acidification discussion is the fact that the shellfish growers were the ones that brought it most to light. And those shellfish growers, many of them are, well, I'll just say they're all across the political spectrum. So it isn't just people who want to go and conserve and the environmentalists that saying like, ooh, oh wait, it's bad. No, now you have people that are providing jobs, people who are Democrats and Republicans, people who are making their livelihoods and their families. And all of those people were saying like, wow, we got to get on top of this. And so I think the more you can have those conversations where you're talking about the importance of the ocean, the importance of food, and really take it out of the contentiousness. So that's what ordinary people can do to help, is to really help educate each other, I think. Of course, your carbon footprint is critical for dealing with ocean acidification. National policies that are going to curb the CO2 emissions and help with climate change. That's all critical. So ordinary people can be extraordinary.
I've got a question. We've already seen a large decrease in the last several years with the number of dig days for razor clamming due to the domoic acid. With the projections with OA, do you see that becoming a factor in like harvestability too?
That's exactly why we're really trying to research the harmful algal bloom nexus with ocean acidification, and in lab plankton, if they raise CO2 levels, they find that the Pseudonychia cells produce more domoic acid and that there's more of them. So, but, when we had that big Pseudonychia bloom, that was during the marine heat wave, right? The one that shut down fisheries from Alaska to Baja. So it's multiple stressors, but not only did you have the marine heat wave, but you had a preponderance of surface water that was getting that atmospheric CO2 signal as well. So it's a tangled web, Geraldine. But I feel that we have all of these stressors that are going to be increasing with time. And so that's going to be ocean acidification. That's going to be the odds of marine heat waves developing. That's going to be the just the background temperature as well. And so yeah, I think it's a real potential. Mm-hmm. Yeah.
All right, so it looks like it's after 7:30. So to respect everyone's time, I think we're going to call it here. But I really want to thank you again for being available for this tonight. And I really enjoyed this presentation, how you framed everything with like the historical process of all of the different monitoring and groups that have been developed in the last several years. So yes,
Thank
thank you
you.
again, and thanks everyone for joining.
It's been my pleasure, and I wish I was in an audience where I could see everybody, but thank you so much for letting me into your homes, and it's great to connect with you all. And thank you, Geraldine, for the work that you do to bring this kind of conversation to everybody. So thanks.
Absolutely. Have a great night, everyone.
Bye.